So now that we have understood the concept of center of mass, how we find out the position of center of mass, the velocity of center of mass, and as well as its acceleration, and also having understood the fact that when there is no external force acting on a system, in that case the velocity of the center of mass remains a constant. Using these now, we can talk about a new principle which we call as the conservation of momentum, which is a derivation from the previous result itself, the aspect which says that the velocity of the center of mass does not change if there is no external force acting on them. It is just another form in which we can represent the same result, and this result we call as the law of conservation of momentum. This law is used in all places where particles interact with each other without any external force coming into picture between them. They interact due to their own internal forces, because of which when we see that there is no external force acting on the system, we can say that even though the system particles are undergoing some change in their velocities and their accelerations, their center of mass, because there is no external force on the system, there will be no acceleration with the center of mass, so that the center of mass will still have the same velocity, and this we now express in terms of the momentum of the system. So let us see how it works. So we all know what momentum is, right? Let us now define momentum for an extended body. Let's say for an n particle system. For n particle system, can we say that momentum, which we know by definition is written as P is equal to m into v. This is a vector relation, momentum and velocity point in the same direction. Can we say for an n particle system, the total momentum of the system, P total of the system, will be nothing but the vector sum of all the single momentums of each particle that the system consists of, right? So can we write the total momentum of the system as m1 v1 plus m2 v2, and we go on doing this till we reach the last particle, the nth particle, mn vn. Mind you, this is a vector addition. We are adding the momentums vectorially, right? So now, do we understand that we can modify this expression by doing a small change in it? Let us multiply this whole expression with capital M, where capital M is nothing but the total mass of the system, and divide it by capital M. If we do this, and now if we take this capital M beneath this whole expression, see what are we getting? We will get m by m into m1 v1 plus m2 v2 plus so on up till mn vn whole divided by capital M. Capital M, understand that is nothing but m1 plus m2 plus m3 and so on. Do you see this relationship? This relation that we have obtained is nothing but the expression for the velocity of center of mass of a body or a system of n particles here in this case, right? So can we say that we can write the total momentum of a system as the total mass of the system times the velocity of center of mass of the system, a very important relation. Now, once we understand that the net momentum, the total momentum of a system is associated with the velocity of center of mass, can we go back to the same condition that we discussed in the previous exercise, previous video, where we said that if the external force acting on a system is 0, this means that its velocity of center of mass does not change with time. The center of mass moves with constant velocity. Now, if we use this result in the above expression, what do we obtain? Do we obtain that it means that the total momentum of the system also remains conserved? That also remains a constant. That also does not change with time, right? What is the total momentum? The total momentum is the mass of the whole system times the velocity of center of mass, which is nothing but m1 v1 plus m2 v2 plus up to mn vn. This total momentum of the system remains constant under the case where there is no external force acting on the system. It is this expression that we have written over here, this particular expression, that we call as the law of conservation of momentum. Law of conservation of momentum. So what do we understand from here? We understand that if there are particles that are interacting with each other, but there is no external force coming and acting on them, in that case their initial total momentum will be equal to their final total momentum. For example, as we have drawn this figure above here, let's say these are two particles, two balls, let's say of masses m1 and m2, which are initially moving with velocities u1 and u2. Now, when they move together, it so happens, let's say that u1 is greater than u2, so that m1 approaches m2, m1 comes closer to m2 in time, and the two bodies collide. So, let's say this is the situation where they collide with each other. When they collide, they will exert forces on each other, the force of collision. But understand that if we consider both the balls as one single system, there is no external force acting on this whole system of two balls, which means that the net momentum of the system should remain conserved, which means that the initial momentum of the system, which will be nothing but m1 u1 plus m2 u2, right? Can we write that as the initial momentum? Should be equal to the final momentum of the system of two balls. Now, after collision, if we assume that the new velocities that the two balls acquire are v1 and v2, can we say that their new momentum will be m1 v1 plus m2 v2? So, for this above relation, by the law of conservation of momentum, we can write m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. This is the expression for law of conservation of momentum for a two particle system which is interacting with each other with no external force coming and acting on the system. This expression is such is a very important expression. We shall be using this expression quite often, especially in the topic of collisions, which we shall be taking up next. There we shall see that two bodies, when they collide with each other, they do exert forces on each other. They do interact with each other through forces, but those forces are equal and opposite in nature. They are like internal forces. There is no external force coming and acting on the system, and hence we can say that the external force on the system is 0, which would mean that the total momentum of this system of two particles, colliding particles, will always remain conserved or constant, whatever you want to call it. Okay. So, how do we use it into questions? How do we understand situations based upon the law of conservation of momentum? Let us look at a few examples now. The first example could be that of, let's say, a bomb. A bomb is a body that can explode from within, right? That's why this example. A bomb can explode from within, so that when it explodes, it shatters into particles. It creates many particles out of it, and all those particles will move in various directions with various velocities. So, just for the sake of convenience, let us consider a case where this bomb, which has a certain mass, it explodes from within, and it just explodes into two particles. It explodes into two particles, one of mass m1, which after explosion moves towards right with a velocity v1, and another mass m2, which moves towards left with a velocity v2. Okay. We are supposed to get the relationship between v1 and v2 if we know the masses m1 and m2. Understand that the bomb will have a mass of m1 plus m2, right? If it is giving out these two particles only. Can we say that when the bomb was at rest, initially, its momentum was 0? Can we say the initial momentum of the system of bomb is 0? So, since the bomb exploded from within, there was no external force that came and acted on the bomb to bring about the explosion. Can we say that the external force on the system has been 0? External force on the bomb is 0, which means that the momentum of this bomb system will remain a constant. It will not change with time, which means that if the initial momentum of the bomb was 0, its final momentum will also be 0. Finally, what is the momentum of the system? Do we see that from this equation we can write the initial momentum P initial is equal to P final. This will imply initial momentum is 0. What is the final momentum? Can we say the final momentum will be m1 v1, the momentum of the first particle, minus m2 v2, because v2, okay, let us not take it to be minus. If we are trying to write a vector equation, let's write m1 v1, vector v1, plus m2 v2. Right now, we are not taking any assumptions about the directions of v1 and v2. We shall get it from this result itself. Do we understand this expression will give us the final momentum of the two particles created out of the bomb? right? And can we say their net momentum must be 0 because initially the momentum of the bomb was 0. Now from this expression, what are we getting? Do you see we are getting m1 v1 is minus of m2 v2. What does that mean? That means that the momentum of the first particle should be just equal and opposite to the momentum of the second particle, so that when we add the two momenta, they add up to give you a 0 value, right? Or let's say if we want to find out one velocity in terms of the other, can we say from here we can also write v2, let us say, is equal to minus of m1 v1 by m2. See that a little bit of mathematics will give us this result. What does this tell us? It tells us that the velocity of the second particle is just opposite. The minus sign here tells us about the direction of the velocities, right? It is telling us that the particle m2 moves exactly in the opposite direction to the velocity v1. The only thing is their magnitudes are related to each other with this particular constant factor, which can be determined if you know the two masses in which the bomb has been exploded. So understand this fact very carefully. This is an important method of solving questions which are based upon the law of conservation of momentum. You can find out the magnitudes as well as the directions of the momentas as well as the velocities of particles that are being studied through this. Another example could be, let's say, that of a projectile. Let's say there has been a projectile which is projected from the origin, like we have studied projectiles, right, in the chapter kinematics. Let's say this is a big projectile which has been projected with an initial velocity u, making an angle theta with the horizontal. We all know that it will go and take a path like this, a projectile path, the parabolic path, right? Now in this case, let us consider the case that this projectile breaks into two particles at the top. When it reaches right here at the top, it breaks into two particles of equal masses. So for the sake of convenience, let's take the mass of this original particle as 2m. So this particle 2m, when it reaches here at the top, it breaks into two m's, one m here and the other m here. According to the situation now, if it is given to us that let's say one of the masses m, it retraces its path back. It moves back through that path from which the original particle came. So knowing this, we are supposed to find out the velocity with which the second mass will move forward. Let's understand this question carefully. The question says that the particle which is projected with a speed u with an angle theta, as it reaches at the topmost point, it breaks into two identical particles, one of which retraces its path back to the origin. We are supposed to find out the velocity of the second particle soon after the explosion takes place. Now understand what happens here. Do we see that the moment the explosion takes place at the highest point, at that highest point, the velocity of this mass 2m at this point would be u cos theta. Do we all know this from the information of projectile motion? At the highest point, it is only the x directional velocity that the projectile has, right? So what is its initial momentum? P initial of this particle just before explosion will be 2m into u cos theta. Can we say this? Yes. Now, at the moment the explosion takes place, the particle was moving horizontally. Do we understand that initial momentum is all horizontal? Right? And if you look at the situation carefully here, horizontally there is no force acting on this particle. All the force that's acting on a projectile is g in the downward direction. Like the acceleration is g in the downward direction, the corresponding force is mg, right, which is vertical in direction. So horizontally there is no force. So can we say that the F external along the horizontal, along the x direction is still 0? So we can at least use the law of conservation of momentum along the horizontal. Can we still say that the total momentum along the horizontal then should be a constant? Along the vertical it may not be constant because there is a force acting along the vertical. But along the horizontal, the net momentum will still be conserved. So this is the initial momentum, right? What is the final momentum of the system? For the final momentum, do you understand that some information has been given to us? This small mass m, if it has to retrace its path back to the origin, what do you understand about the velocity with which it starts moving towards left? don't you think it will be the same velocity with which the particle 2m just reaches at the top, u cos theta? So small m, as it moves backward to retrace its path and reach back to the origin, it will start with the same speed u cos theta but in the opposite direction, right? So for one of the masses, we know that its velocity is u cos theta. If we assume that, let's say, the second particle has a velocity v in the other direction towards right, because we know now that the net momentum has to be towards right, along the rightward direction horizontally, right? So we expect the velocity of the other mass to be towards right. Now all we need to do is, we need to write the expression for final momentum again towards right, which will be, for the mass, second mass, it will be m into v, whereas for the first mass, see that m into u cos theta is pointing towards left. If we are taking rightward direction positive, that means this momentum will be minus m into minus u cos theta, isn't it? Because the velocity is leftward, we need to put it with the correct sign. Momentum is a vector quantity, we need to take care of the directions when we are substituting the values, right? So this is the final momentum, maybe we can just write it mv minus mu cos theta, right? And now all we need to do is equate these two momentas, knowing that along the horizontal, the momentums does not change. Pi is equal to Pf gives us 2m into u cos theta is equal to mv minus m into u cos theta. Can we solve this for the value of v? See that m cancels out throughout, and we can bring this minus u cos theta in the on the other side to get v is equal to 3 times u cos theta, right? So this is how we can actually find out the velocity of one of the particles if the velocity of the other particle is known. See that we have simply used the law of conservation of momentum here. Okay. Now another example that we can take up related to this. Let us take up another case. The third example is, there is a man who is standing, I have taken too long, a man who is standing on a platform, let us say. This is a platform of mass capital M. So the mass of the man is given to be small m, and the mass of the platform is given to be capital M, and the platform itself is kept on smooth surface. Let's say it is ice on which it is kept, which is absolutely smooth. Smooth ice. Smooth ice for the fact that there will be no friction coming from the surface of ice and acting on the platform, which means there is no force from the ground acting on the platform. Now the question is that if the man starts moving on the platform with a speed v relative to the platform, with what velocity relative to the ice does the platform recoil? Okay, I'll just repeat the question. A man of mass small m is standing on a platform of mass capital M kept on smooth ice. If the man starts moving on the platform with a speed v relative to the platform, with what velocity relative to the ice does the platform recoil? What do we understand by recoil? As the man starts moving towards right, it is found that the platform will move towards left. This process of moving in the backward direction is called recoil. Now why will the platform recoil? The platform will recoil in order to keep the momentum of the system of man and the platform unchanged. Why will the system's momentum remain unchanged? Because this whole system of man and platform together is placed on a smooth surface which cannot exert any force. So the external force on this system of man plus the platform is 0, which means that the momentum, the total momentum of the man plus the platform system will remain constant, which in this case is 0. Why 0? Because initially the man was simply standing on the platform. So can we say this constant value of momentum is 0? Initially the man was at rest, the platform was also at rest. So both of them had their momentum 0. So initial momentum of the system is 0. So should be the final momentum. Finally, when the man starts moving towards right, in order to keep the momentum of the system still 0, the platform will start shifting towards left. Okay, so it is the leftward velocity of the platform that we are supposed to find out. So let us assume it, right? If we assume that, let's say the platform moves towards left with a velocity of Vp. First thing is, we are supposed to get the actual velocity of the man with respect to the ground, with respect to the ice, the surface which is at rest. Why so? Because in the question, this V value that they have given is not the actual velocity of the man with respect to the ground, it is the velocity of the man with respect to the platform. V is the velocity of the man with respect to the platform, the relative velocity. So from here we first need to get the actual velocity of the man. How do we get that? We use the definition of relative velocity. We know that by definition, the velocity of man with respect to the platform should be the velocity of the man minus the velocity of the platform. This is a vector subtraction, right? This is how we get the relative velocity, right? From here, can we write velocity of man is velocity of man with respect to the platform plus the velocity of the platform? Vector addition, right? Now look at this carefully. Can we say that the velocity of the man, when we write velocity of man with respect to the platform, is given to be V towards right? See that we have taken rightward direction here first. So let us consider rightward direction positive. Corresponding to that, when we write the velocity of the platform here, added to this, the velocity of the platform is towards left. Leftward velocity has to be taken with a minus sign because we are considering rightward velocity positive. This is the vector addition that we are doing, right? So velocity of man with respect to the ground now comes out to be V minus Vp. Okay, so we have to get this value before we could start with using the law of conservation of momentum. Now we can use the law of conservation of momentum, saying that by conservation of momentum, the initial momentum should be equal to the final momentum of the man plus the platform system. Initially, the man and the platform both were at rest, so their initial momentum was 0. Finally, the momentum of the system will be the mass of the man times its velocity, V minus Vp, right? Mass of man into velocity of man gives us the momentum of the man. And added to this, the momentum of the platform. Now see that the platform is moving towards left, so its momentum will be negative, right? Minus mass of platform, which is given to be capital M, by the way, capital M into Vp. This is the leftward momentum of the platform. So when we are adding momentas, we have to add them vectorially. From here, do we see that we can easily obtain the value for the velocity of the platform? See that from here we can write 0 is equal to m into v minus small m plus capital M times Vp. And from here now we can easily write Vp is equal to mv over m plus m. Okay, this is the velocity of the platform towards left. Let's take up another question related to same, the law of conservation of momentum. Another example is a bullet of mass 50 grams is fired from below into a bob of mass 450 grams. So what is the situation? We have a bob of a pendulum like this, which is hanging from a certain support, and a bullet comes and hits this bob from below. Okay, the masses of both the bullet and the bob are given to us. So a bullet of mass 50 grams is fired from below into the bob of mass 450 grams of a long simple pendulum. The bullet remains inside the bob and the bob rises through a height of 1.8 meters before coming to rest, before reaching its highest point. We are supposed to find out the speed of the bullet just before hitting the bob. So what is happening here? This bullet, which because it is moving with a certain velocity, it goes and penetrates into the bob and remains within the bob. Okay, due to which the bob and the bullet system will acquire a certain velocity, due to which they will start moving upward, and as they move upward, they will slow down under the effect of gravity and they reach till a certain height, where they stop for a moment and then again start moving down. So this height till which they move is given to us as 1.8 meters. Okay, from knowing this, all this information, we are supposed to find out v, the speed of the bullet with which it pierces the or penetrates the bob. Just before it penetrates the bob, what was the velocity of the bullet? Now let us understand what is happening. The bullet comes from below. It carried some momentum with it, right? It has a mass and it has a velocity also. Can we say, if we assume that the velocity of the bullet just before hitting the bob is v, what will be the initial momentum of this system of bullet and bob? Can we say P initial will be only the momentum of the bullet? It is only the bullet which is moving initially. So it will be m into v, the mass of the bullet, times its velocity with which it hits the bob. That's the initial momentum of the system. Now as the bullet penetrates the bob, it becomes a part of the bob. In the process of penetrating, it will exert some force on the bob, understand this? But if we consider the bullet as well as the bob as one single system, do we see that that force that the bullet exerts on the bob will be an internal force? No other external force acted on the system during that instant when the bullet penetrates the bob, right? So can we say here in this case, the net force on the system would be 0 at the moment the bullet penetrates through the bob. At that instant, understand that this is an instantaneous event. It happens in a very short span of time. Now some of you might feel that there is a gravitational force acting in this direction, in the vertical direction. There is a gravitational force acting on both the masses, so there is an external force. But this is a special case that you need to understand, that whenever changes in the state of the bodies happen in a very short span of time, it's an instantaneous change that happens. In that scenario, in all those cases, those forces which are of constant value and are acting on the systems throughout, they can be neglected for that very short span of time. You'll understand this better when we discuss the concept of collision and we go through questions which incorporate all such cases in collision. Here in this case, as the bullet penetrates the bob, though there is a constant force of mg acting on both the bodies, since this process of penetration is a very, very fast process, it's an instantaneous process, we can neglect the presence of gravity at that moment. So we can say that the external force is still 0, so that the total momentum of the system, P initial, will be equal to the P final. The momentum of the system will remain conserved just before and just after the event that is under discussion. What is the event here? The event is the penetration of the bullet into the bob. Okay, so can we say, if after this process, if after this event, the bob as well as the bullet, they start moving up with a new velocity v dash, then the final momentum of the system just after the penetration will be the mass of the bullet plus the mass of the bob times v dash, right? And can we say, from law of conservation of momentum now, we can write m into v is equal to m plus capital M times v dash, isn't it so? And from here we can find out the value of v dash in terms of v. Can we write v dash is equal to mv by m plus m? At this point we can substitute all the values of the masses because the masses are known to us. Small m is 50 grams, which we can write as 0.05 kg, divided by 0.05 plus capital M is 450 grams, which we can write as 0.45 kg, right, into v. See that this will be 0.05 by 0.5 into v, which will be nothing but v by 10. So what are we getting here? V dash we are getting as v by 10. This is the velocity with which the system starts moving soon after the penetration of the bullet takes place into the bob. Now as the system starts moving up with a velocity of v dash, as it moves up, gravity will work on it, and there will be an acceleration due to gravity g acting on both the masses in the downward direction, and the system will slow down till it reaches the highest point where its final velocity v final will become 0, right? This we know from the concept of kinematics. We have studied this in the previous chapters already. So can we say, for the second part of the motion, the first part was the bullet penetrating the bob and the bullet and the bob attaining a certain velocity v dash. Second part of the motion is that the bullet and the bob system together move up under the effect of gravity and they slow down till they come at instantaneous rest at the top. Now for that part, for the second part of the motion, can we use the third equation of motion, v squared minus u squared is equal to 2as, to connect the height to which they travel up with the initial velocity with which they started off? Can we say from here, final velocity of the system as it reaches to the top will be 0 minus the initial velocity with which they started off, we have considered that as v dash, so it will be v dash squared here, right, is equal to 2 acceleration due to gravity here is minus g, we are considering upward motion, acceleration due to gravity is acting downward, so minus g into h. H is given to us 1.8 meters, we can use this into the question, right. Now all we need to do is substitute the values and solve. So see that v dash we can substitute from here, v dash is nothing but v by 10 whole squared is equal to 2g into h, the minus signs cancel out here, and now all we need to do is get the value of v, which we are being asked to find out. V squared from here will be 2gh into 10 squared, right. Substitute the values and get your answer, 2 into 10 into 1.8 into 10 squared. See that this is v squared. So when you take the square root on both the sides, you will have 2 into 1.8, which is 3.6, into 10 is 36. 36 into 10 squared. This whole thing will be in a square root, and this can easily be taken out of the square root. 6 into 10, 60 meters per second will be the final answer for this question. Understand that the speed that we have obtained here is the speed of the bullet moving up, right. Understand that soon after the bullet penetrates the bob, the velocity of the bob plus the bullet system becomes v by 10, which will be 6 meters per second, and the system of bob and bullet will start moving up with this initial velocity of 6 meters per second, and with that it reaches a height of 1.8 meters per second.